Okay, first on our list of things we can actually put on an alpha position is a halogen. Now, specifically, in many of these cases we're going to be looking at adding a bromine, but I don't want you to think of this as being all that new. You've seen some of this before, specifically with things like this, back in alkene land. We know, without question, how this reaction works, that we end up with a cation on the more substituted carbon, and a halogen on the outside. Well, this is still an alkene. So now we're looking at essentially the same type of example, only if we drew it that way, we'd be here, where we'd have now the bromine where they show it, we'd have an OH here, and we'd have a cation on the adjacent carbon, just like this. And then either we resonate in to give us this intermediate, or we let water take the hydrogen to give us the product. So we could draw this pathway slightly differently. It's not wrong either way, but what I'm drawing it this way specifically is to keep your mind on the fact that this is still an alkene reaction. It's an alkene reaction, but instead of what we saw back in the alkene chapter, where we had to have some other electron donor come in to take care of the cation, now it's right here. It's already attached. So I don't need another nucleophile to come in if I have something adjacent to the cation that can donate a pair of electrons more quickly, more readily. And that's why they're showing the intermediate that we have here in the middle. So what happens if we have two different possibilities? And there's the problem. Except for really simple examples, the two sides are not going to be identical. And if they're differently substituted, like this case, we have a question. What's going to go and where? What's going to go where, and which one's going to be the dominant product? Usually the question comes down to which alkene is better and more stable. In this case, the one on the left, this is a more substituted alkene, which means more hyperconjugation, therefore a more stable alkene. This on the right, less hyperconjugation, a less stable alkene. And so what we see with the products, this is the major product coming from this alkene. That tells us that this reaction is basically working with thermodynamic control, that we're looking at a reaction producing largely what is the thermodynamic product. Much like what we saw back in the dyings chapter, we can sometimes control that trade-off between thermodynamic and kinetic control and switch up the major and minor products. Your book doesn't address that in this chapter. I'm going to take their lead on that, but it is possible to tweak conditions and help this ratio a bit. You can probably guess how you would do it. Okay, so uses. If we have a halogen here, then we can actually do an E2 reaction and create a conjugated alkene. So the alpha bromination, like I said, putting a bromine in place is generally just so you can knock it back off either with substitution or an elimination. This is a good example of that. We have a lot of uses for this alpha-beta conjugated system. So if we have something like this, this is the alpha carbon, the one we've been working with, the one directly down from that is beta. So when we talk about an alpha-beta unsaturated system, we're going to have a lot of things we can do that are unique to that. Which has a lot to do with the type of stuff that we did back in the dying chapter, only now we have a polar atom at one end of it. So at a certain point in the chapter, you're going to have to go back and look at that stuff if you don't have a good memory of it, because it's going to come back and haunt us. All right. Doing this with a halogen, doing this with the carboxylic acid is a little bit more difficult because of the acid side. We don't want to make the acid bromide. Just putting a Br here, well, that's what this would do. The reaction doesn't work very well if I don't have that. So we're going to temporarily make the acid bromide. So that's what this is. We're temporarily making the acid halide. We're temporarily making an acid bromide, usually. Again, as I said, most of the time we're doing these with bromides. It's a good leaving group, but not so good that I have to worry about storage and stability. Then, with this acidic hydrogen out of the way, we can work with this one. With the OH group present, I really can't deprotonate the next door, the alpha carbon, so I have to cover it up, and then, because acid halides react easily with water, I can get it back at the end. So this is a very unique temporary protecting group. Normally we don't make things more reactive and call it protection. That's a strange terminology, but it's correct in this case. We're covering up a less reactive group in general for something that's less reactive towards any type of deprotonation. There's no proton when I replace that OH with a bromine on that atom, so I don't have to worry about it being deprotonated. So I'm still technically making something that is less reactive and therefore protected. And then we're going through the same type of bromination that we did in the previous slides. Only at the end, we're going to wipe out that last halogen, the acid halide, by rehydrolyzing it back to the carboxylic acid. Okay, basic conditions are a little bit more interesting and a little bit more problematic. And here, if we're under basic conditions, we're dealing with an enolate. So as I said, I don't know what your book was talking about with saying that the base conditions could be an enol. So we get a better nucleophile out of it. The enolate is a better nucleophile because it's anionic all the time. And you would think this would be ideal. If someone says that, you know it's not. Why? Because we have a problem. And here's the problem. Once we've done it, once we've taken one molecule of our alpha substitution, well, this had a certain level of acidity because it was being pulled on by the carbonyl. Still the case here. But now it's also getting yanked on by the bromine. So this is more acidic. Which means the next base that comes in is going to have a decision to make, and it's going to go here. Which means that if it's possible, we're going to end up with polyhalogenation. And this is even more acidic still, so we're going to end up continuing the process. So base catalyzed has its problems because we can actually do it a second and particularly a third time. Now, they don't explain that. I did it out of order slightly, but the point is polyhalogenation is a problem. If you wanted to make a single bromide because you're going to do something like that elimination that we saw for the acid catalyzed case, this is really not a good method to do that. It's more likely to be problematic. You can't really control this with stoichiometry. This is more kinetically controlled, so you really don't have much you can work with to stop it. But if you take the extreme case where we're now going to do this 3 times, we have 3 hydrogens here, and this is kind of what I was drawing before, that it's going to go once, then the second one's going to be faster than that, then the third one's going to be faster than that. Then we're going to get to this case. We're going to get here. There's no more hydrogens. No more alpha hydrogens to play with, but hydroxide is not just a base. It's also a nucleophile. And normally, a carbon group is not a decent leaving group, but it is once you stick 3 halogens on it. So that's how we're going to get here. And the leftover, after the reaction's over, is bromoform. So it's called the haloform reaction because this is halo. So in this case it's bromoform. If there were chlorides, it's chloroform. 3 chlorines on a carbon with 1 hydrogen is a haloform. So that nucleophile part is essentially what we saw in the acyl substitution chapter, but with a unique leaving group. This is not one we talked about in that chapter. It really only works because it is so electron poor, because there are 3 halogens on it. It's then going to turn around and take that hydrogen to form bromoform, and then we're not going to get a hydrogen on this until the reaction's over, and typically we dump in dilute acid afterwards. And then we're going to get our actual carboxylic acid product out of it. So if you notice, that's what they gave as a second step here. That's why. Because this is basic enough to take the hydrogen off of here, what they're showing in this mechanism down here. This is resonate and stabilized, so it's not getting protonated without a real acid being put in place. So that's the second step, the final step. Essentially, this would be done probably in a separatory funnel just to isolate things. It's not really a step in terms of having to set anything up, but you dump in acid at the end to actually take care of the rest of the mechanism.